Hello everyone. In this video we will continue to examine topic 4.4 wave behavior, and in particular we will continue to examine double slit interference and path difference and focus in on sort of the quantitative analysis of the double slit experiment. All right, so let's put the ideas that we have discussed in the previous videos together. We know that coherent plane waves, okay, so that's our laser light coming in. It can be modeled as plane waves. Why? Because these slits are very small and very close together. So the light that comes in is sort of a flat wave of light coming in that then hit the slits. And for reasons we'll discuss a lot later, they diffract through the slits, although we've seen diffraction before. So remember that if the wavelength is roughly the size of the slit, as it is in this diagram here, you can see a very clear diffraction effect. So they diffract through the slits. And then here's the key. We get bright lines where the path difference between the two waves is exactly equal to an integer number of wavelengths. So if that path difference is 0, as it is for the central maximum, then you can see that the waves overlap there, okay? And because they overlap, you get constructive interference, and that central maximum is known as the first order, or actually, in particular, the 0th order maximum. So it is the central maximum where the path difference is 0. Where the path difference is exactly equal to 1 wavelength, okay, that would be this set of lines here. You see where those purple wave fronts overlap? Those are points of constructive interference as well, and so that is your first order maximum where the path difference is 1 wavelength, or 1 lambda. Notice this pattern continues for the second, third, and fourth order wavelengths, okay? Now, this is super tricky. They also undergo destructive interference, as we discussed, but where they undergo destructive interference is often confused by students. So let's focus in on this. You get constructive interference where these wave fronts overlap, right? You see them here, 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 and so on and so forth. And you get constructive interference again where they overlap again. So if you see them overlapping again, all right, you know that you're going to get constructive interference all the way along that line, even if that screen were closer or further away. But you get destructive interference where you see this zigzag, and that's a little bit tricky. So I want to focus in on that. In this region where there's a zigzag, you can see that one of the waves is here, and one of the waves is here. And so at those 2 points, right, that particular wave front, or wave source, is at a peak, trough, peak. Remember that we think of the wave fronts as indicating the location of the peak. And the other wave, you'll notice, the other wave is at a peak, okay, that's the wave front in between, okay, that is exactly halfway between the other 2 wavefronts. And so because one of the waves is at a peak exactly halfway in between where the other wavefront is, then a line of destructive interference would go exactly in between the line of constructive interference. So anytime you see that zigzag, that's the point where you're going to get a dark spot here. So you get a dark spot in between those bright spots, right in the center of sort of that characteristic zigzag. All right. Notice that the intensity of that central maximum, so the brightness of that central maximum, is proportional to the amplitude of the wave squared, and so therefore you're getting 4 times the original intensity of the wave. Because it's proportional to the amplitude squared, the central maximum is double the amplitude because you're getting the amplitude of both waves, and therefore the intensity of the light on the back is 4 times the intensity of the original wave coming in. In the next video, we will begin to sort of unpack more this mathematical relationship that we can use to characterize the fringe spacing.